Good morning. This is P. Venkata Mahesh, Assistant Professor in Mechanical Engineering Department, Institute of Aeronautical Engineering. So, this class, what we will do in the last class, what we have seen is the general idea of the finite volume method, and the finite volume method is a topic in computational fluid dynamics meant for the 6th semester mechanical engineering students. Now, in this class, what we will do, how to implement the finite volume method. So the implementation of finite volume method we will see in this class. So the finite volume method. The finite volume method, as I already discussed, the finite volume schemes are generally categorized. The finite volume method, what we have seen is we use the integral form directly on the domain. Okay, the domain is discretized into nodes, and on the domain directly we use the integral forms. By transforming that integral forms into algebraic forms, we directly apply them. So how to do that procedure? So we have two approaches in finite volume method for doing this. So one is cell-centered approach or scheme, other one is node point scheme or approach. So for illustrating these two procedures, what we are going to use is one equation. This is the modal equation that we are going to consider. So the equation is like that. There is this dou phi by dou t, dou e by dou x, dou phi by dou y is equal to 0. So this is the governing equation that we are assuming. This is the generalized governing equation that we are assuming, and we are trying to use this equation for illustrating the finite volume procedure. So first, what we have to do, the equation is integrated over the domain. Okay, so this is the domain, and what we have to do, I have to integrate this equation over this domain. So what I am doing, I am keeping all the time differential one side and the space differential one side, and I am integrating this equation over this domain ABCD. Okay, this domain is ABCD, and I am integrating this dou phi by dou t over ABCD, and I am integrating the sum of dou e by dou x, dou f by dou y over the volume ABCD. So the entire domain I am trying to integrate. Now what is this ABCD? That let ABCD is a positively oriented, smooth and simple closed curve in a plane. So it is in one plane. So it is a two-dimensional object, and D be the region bounded by the ABCD. So whatever region is there in between, this is defined by capital D. So this is the this is what we are considering. Now if E and F are functions of x and y, okay, E and F are functions of x and y. In the governing equations we have E and F, and that E and F are functions of x and y defined on the open region containing D. Okay, so these are defined on the open region containing this volume, this area D, and have continuous partial differential. So these two are continuous. So the E and F are functions of x and y, and they are continuous partial derivatives. So in such case, what this Green's theorem states is dou E by dou x plus dou f by dou y integral over ABCD can be expressed as the cyclic integral over ABCD in of E dy minus f dx. Okay, here E is differentiated by x and f is differentiated by y. Because it is continuous, what I can do is I can multiply this. I can cancel these two, and E will have only dy, and I can cancel dy here, and I will have f here. Okay, when it is possible when it is a continuous partial derivative. Okay, it is these functions are having only if these functions are having continuous partial differentiations, then only we can use this Green's theorem. Now if I substitute this, okay, the value of this, which is this, in our previous equation, what will happen is the equation becomes like this. So integral over ABCD dou q by dou t into dx dy is equal to minus integral ABC over ABCD e dy minus f dx. So this is the equation that we have arrived at. Now we'll take this equation and we'll apply the nodal point method and cell center method. Okay, we'll apply these two methods and see how to how to apply this finite volume method using these two approaches. So the first one is cell centered approach or scheme. So what is this cell centered approach or scheme? So here in this cell I have one node, and here one node is there, one node is there, one node is there, one node is there. So in the center of this D I have a node. So this is called cell centered scheme. So the integrals of in the equations are approximated over the element. On this element we have to write an approximate equation for this integral equation. So the dependent variable q is to be solved for node 5. So here what is the node? This is the node in the center of the cell, that is 5, and we have to solve this q. We have to solve for q over this node which is located at the center of the element, and the scheme is referred to as cell centered scheme. So this ABCD, okay, the ABCD is there, and in the center of this ABCD I have my 5. Because 5 is in the center of the cell, it is called cell centered scheme. The formulation can be expressed either in explicit form or implicit form depending on how E and F are evaluated. So as we have already discussed in finite difference method, here also it can be an implicit form or an explicit form. We'll see that. Now this is the equation that we have, and in this equation what we have to do is we have to write a discretization equation. Now here it is a time derivative. So it is, since it is time derivative and it is done for the node 5, it is q5 n plus 1 and q5 n. Okay, so the distance between two time steps is n plus 1 and n time steps, and that the time interval is delta t. So in this way I transfer this differential into this term into this equation. Okay, now what I have is e dy minus f dx. So this should be applied on the entire ABCD, and we have to apply this equation over ABCD. So how to do that? EI, so this is one node here, 2 node, 3 node, 4 nodes. So 4 nodes are there, and EI delta y AB. So this this is the length of the element AB, and delta, that is delta y AB, and E of I into this length. Next E of j into this length. Next E of m into this length, and E of n into this length. So the y coordinate of this length I am taking. Now plus f into dx, the x coordinate. So fi into the x coordinate of this length, and fj into x coordinate of this length, and fm into x coordinate of this length, and fn into x coordinate of this length. So like this I have transformed this integral equation into this algebraic equation. Now here in this equation, ABCD is the area of the cell. So this cell ABCD is having some area, and that is given by ABCD. And points I, J, M, N represent the midpoint location of edges ABCD, AB, BC, CD and DA respectively. So this is obvious. So between A and B, okay, the edge AB is there. The edge AB, the midpoint is I. Edge BC, the midpoint is J. Edge CD, the midpoint is M. The edge DA, the midpoint is N. Okay, like this we have taken I, J, M, N. We have taken. Now this is the equation that we have arrived at. Now for points 1, 2, 3, 4 and 5 are called the control points of the 5 quadrilaterals. Okay, 5 quadrilaterals are there. So here one quadrilateral will be there, here one quadrilateral will be there, and here another quadrilateral will be there, here another quadrilateral will be there. So for these 5 quadrilaterals, here 1 is the control point, here 2 is the control point, here 3 is the control point, here 4 is the control point, and here 5 is the control point. And we have this this ABCD is surrounded by 4 quadrilaterals, and for these 5 quadrilaterals we have taken the control points as 1, 2, 3, 4 and 5. Now X and Y increments of each edge are determined by following relations. So how to find the values of delta X, delta Y AB, delta Y BC, delta X AB, delta BC and so on. So that is illustrated here. So if I know the coordinate, if I know the Y coordinate of B and if I know the Y coordinate of A, then delta Y AB is equal to Y coordinate of B minus Y coordinate of A. Similarly, if I know the X coordinate of B and X coordinate of A, then delta X AB is equal to X coordinate of B minus X coordinate of A. So similarly, if I know what is X coordinate of C and X coordinate of B, delta XC, delta XBC is equal to X coordinate of C minus X coordinate of B. Similarly, if I know what is the X coordinate of D and X coordinate of C, then delta X CD is equal to X coordinate of D minus X coordinate of C. So it is very simple. Say suppose this is the length. So the length is given by say suppose 1 and 2 are there. So the distance it is equal to x2 minus x1. Okay, delta x is equal to second coordinate minus first coordinate. So the same thing we are applying here, and we are saying that delta x AD is equal to XA minus XD. Okay, so DA we are taking, so it is from A to D. So here from A to B we have taken, so it is B minus A. So if I am taking BC, it is C minus B. If I am taking CD, it is D minus C. If I am taking DA, it is A minus D. Like that I can calculate these values of delta XY, delta XAB, delta XBC, delta XCD, delta XDA, delta YAB, delta YBC, delta YCD and delta YDA. So once I can calculate these values, I can substitute in that and find out the values. Now, what are the values of functions E and F? So we have seen how to calculate what is delta YAB, delta YBC, delta YCD, delta YDA, delta YAX, like that. Now what we will do, we will see the values of functions E and F at midpoints of these edges. How to calculate these values. Okay. Now EI is the midpoint between between 2 and F. Okay. So I is in the middle of 2 and F. So in such case, EI is equal to average of EF and E2. And similarly, EJ is in between 3 and 5. So, for finding EJ, I have to take the average of EF and E3. Similarly, M is in between 5 and 4. For calculating EM, what I have to take? I have to take average of 5 and 4. And N is in between 1 and 5. So, for calculating E1, En, what I have to take? I have to take average of 5 and 1. So, like this, I have to take averages of these values of E for cells 5 and 2 to get the value of E for I, because it is in middle of this cell 2 and 5. Now, these are the things I have. Similarly, I can find what is F. So, for if the property of F at I can be taken as average of the value of cell 2 and cell 5, and average of, for J I can take average of 5 and 3. For M I can take average of 5 and 4. For N I can take average of 1 and 5. So, like this, I have to take the average values of E1, EI, EJ, EM, EN, FI, FJ, FM, FN. So, like this one I have taken. Now, what is this star indicating? Okay, what is this star indicating? So, this it can be of level time interval n, or it can be of time interval n plus 1. Okay, it can be of time interval n, and if it can be of time interval n plus 1. Now, if I take the values of F3, F5 and F1, F2, F3, F5 of at nth level, because nth level is known, it is called explicit formulation. Say suppose if I am taking the values of 1, 2, 3, 4, 5 of F values at time interval n plus 1, because n plus 1th time interval I don't know these values, it will become an implicit scheme. So, that is the difference between explicit scheme and implicit scheme. So, here if I am taking these values at nth time interval, if I am taking the values of E1, E2, E3, E4, E5 and F1, F2, F3, F4, F5 at nth time interval, then it is called explicit formulation. If I am taking these values at n plus 1th time interval, because we don't know these values at n plus 1th time interval, it is classified as implicit scheme. Okay, this is the way we can classify the cell-centered scheme as explicit or implicit approach. Now we'll see what is a node point approach. We'll see next. We'll see what is node point approach. Before that, what is delta x AB? Okay. Now, if this shape is a rectangle, here we have seen that it is not a rectangle. We have taken a quadrilateral element. So, the quadrilateral can be sometime a rectangular element. So, if it is a rectangular element, if it is a rectangular element, so this length is equal to this length and this length is equal to this length. But since this is in this direction, okay, and CD is in this direction, what I have to take? I have to take a minus value here. And here BC is in this direction and DA is in this direction, but we have to take in same direction. So I have to take this one as this. If I take this one as positive, this one will become negative. So like that, delta x AB is equal to minus delta x CD, delta x BC is equal to minus delta x DA. When this happens, only for one case where the quadrilateral becomes a rectangular in shape. Okay, rectangular or square shape. So in such case only the opposite sides are of equal length. Then our problem will become further simple. Therefore, the equation is simply equivalent to finite difference formulation, Hence, the cell-center approximation of spatial derivatives is used. So when I transform this quadrilateral element to a rectangular element, what happens is the finite volume method is becoming equivalent to finite difference formulation. Okay, finite difference formulation, and that too the central difference formulation. It is not forward and backward, it is a central difference approach. The values of E and F are provided by the above equation, may be obtained by other schemes as well. So here we have seen that we are using the central approach. It can also be done by other schemes such as the upwind scheme, like that. Okay, the E and F values can also be obtained by other schemes such as the upwind scheme or downwind scheme. So what is this upwind scheme means? Say suppose this is for here nodes are there, and the flow is happening like this. So if the whole flow is happening like this, I am going up the wind and taking the values, then it is called upwind scheme. Okay. So the next approach is nodal point scheme method. Nodal point approach or nodal point scheme. And this is the integral equation that we have started with for the central point scheme, the cell center approach. So same equation we are taking and starting our nodal point approach as well. Now here in nodal point approach, what we are doing, we are taking the nodes at the intersection of the cells, at the corners. Okay, so A, B, C, D I am taking, and the these are the I, J, M, N. They are same, but these nodes are now at these junctions. So in this approach, the dependent variable is evaluated at the vertices of the element. So previously what we have done, previously we have taken the center, as in the center of the cell, we have taken nodes and we have calculated. Now in this approach, what we will do, the ends of the corners of the quadrilateral, okay, the vertices of the quadrilateral element we are taking, and we are we are using the nodal point approach. The why it is called nodal point approach is we are using the vertices of the quadrilateral for our solution. Now if I want to transform this into quadrilateral, how it will be? QA, this is QA, QB, QC, QD. So for all these things at time interval n plus 1 and QA, QB, QC, QD at time n. That difference I have to take, and since I have 4 nodes, I have to take 4 into the time interval, and this area of ABCD is common. Area of ABCD were multiplied. Now how this will transform? This will be transformed as delta y AB, E delta y. So here for I it is delta y AB, for J it is delta y BC, for M it is delta y CD, for N it is a delta y DA. So like this I have to multiply. Now for X, if I see, for Fi it is delta y AB, for Fj it is delta y BC, and for Fm it is delta y CD, and for Fn it is delta y dA. So like this I will transform this integral equation into algebraic equation. Now this is the equation that we have arrived at, and now what is this EI? Delta y AB, delta y BC is the same, because AB is there. Delta y AB means YB minus YA. Delta y BC means YC minus YB. Delta y DC CD means it is a delta YD minus YC, and delta y AD means it is a delta delta y DA means it is a YA minus YD. So like this these delta y and delta y axis terms are calculated as we have discussed in the cell centered approach. But here the EI and FI, E values and F values are going to little bit different. So here previously EI value is calculated taking the average of the cell 5 and cell 1. But here what we will do, EI value will calculate by taking the average of EA and EB, and EJ value is taken by taking the average of EB and EC. EM is taken by taking the average of EC and ED. EN is taken by taking the average of EA and ED. Like that, I have to take. Similarly, for F also, Fi value is taken by taking the average of E and E, FA and FB. Fj value is taken by taking the average of FB and FC. Fm value is taken by taking the average of FC and FD. Fn is taken by taking the average of Fa and Fd. So like this, I have to take the values of this E and F. Now these values, when I take the values of EA, EB, EC, ED at a time interval n, it is called as explicit formulation. And if I take this EA, EB, EC, ED, FA, FB, FC, FD, these values if I take at a time interval n plus 1, which I don't know, it can be classified as implicit scheme. A conclusion for this class. So in this class what we have discussed is, we have seen that the quadrilateral element we will take and we integrate the governing equation over this quadrilateral, and we use the cell-centered approach or node point approach and transform that into the algebraic equation for further calculation. So if it is a cell-centered approach, I will take the node point here in the center of each cell. If it is a nodal point approach or nodal point scheme, I take these nodes or this node set the vertices of the quadrilateral. So that is the only difference between the cell-centered approach and nodal point approach, which are the basic methods for applying the finite volume method for solving any fluid flow problems or heat flow problems. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.